So moving on with galaxy collisions, we're going to look at computer simulations of galaxy collisions and then Hubble and Spitzer telescope images of galaxies, and realize that what we're seeing in the actual images matches the simulations, and then talk for just a second about the effect that that supermassive black hole has on star formation in the host galaxy. So galaxy collision simulation. So this is a computer simulation. Starts with two spiral galaxies, and over time they move through and collide with each other and then spiral back around. Each time that we have a collision sparks a new round of star formation, which we see in the very blue strings of stars that stretch out between the two galaxies. We see that they collide several times before ending down here in the bottom right as an elliptical galaxy. We notice that that elliptical galaxy has a wide variety of star ages, both population 1 and population 2 stars, which would make sense, because it started out with stars that probably still exist and have moved through several stages of star formation. This entire thing would have taken around 1 billion years. So let's look at galaxies. So we looked at an elliptical galaxy at the end of that computer simulation. Something to note is that elliptical galaxies usually contain very little dust. That makes sense if we have spirals with lots of dust that collide. When they collide, it's that dust and gas that gets condensed into new stars. So several collisions and all the dust gets coalesced into stars. In contrast, we have this image of NGC 1316, an elliptical galaxy with this weird silhouette of dust streaming through the middle of the galaxy. That dust is probably the remnant of a small companion galaxy that was cannibalized about 100 million years ago. That's what we call it when two galaxies collide and become one. We call it galaxy cannibalism, because the bigger galaxy eats the smaller galaxy. So another image of galaxy cannibalism, this is NGC 6240, and this is probably two spiral galaxies that have merged over time, but it's not a complete merger yet. We can tell that because we have down here in these two inset pictures, you can see the glowing centers of those galaxies. Remember that the bulge of a galaxy is held together by a supermassive black hole, and so those black holes are spiraling in towards each other in a death spiral. Eventually they will combine, but that will take hundreds, thousands, millions of years. So another collision. Here we have great evidence that shows that what we see in the sky actually matches that computer simulation. So this image shows 3 of the galaxies in Stephan's quintet, which is actually 5 galaxies. The blue, white, pink galaxy up in the top left is actually not part of the quintet. That galaxy is about 7 times closer to us than the quintet. So of the quintet, there's 5 galaxies. 2 of them are, fairly boring and normal. 2 of them particularly are extremely stretched and pulled and distorted. So we can tell that there have been at least a couple of collisions. 2 things. The streams of new stars go in several different directions. We see this curve, but then we also see this. So those multiple directions on the curves suggest multiple collisions. And in here, the little clumps that are different colors, each of those is a cluster of star formation that occurred at different age ranges, as old as 1 billion years and as young as 2 million. So that also suggests that there have been multiple stages of this collision, that it is ongoing. So we will, continue watching. Starburst galaxies are galaxies where there is, for whatever reason, an extremely large burst of star formation. This galaxy, ILZW096, is only about 500 million light years from us. It's actually one of the closer starburst galaxies to us. This is a Hubble and Spitzer image combined. So the blue shows us visible light from the Hubble, and then the red is from the Spitzer, showing us the infrared radiation. And so the infrared shows us where we have dusty regions of star formation. So we have star formation here in the center of this galaxy, and we have pieces of it over here as well. And then this red is dust. So this starburst galaxy probably is actually a galaxy collision that has progressed so far that we are confused and simply call it an irregular galaxy. We have collisions happening all the way, back through time. We look at this Hubble image of a cluster of galaxies. This cluster of most of them are the orangey galaxies, and they are at various different orientations, but they're all about 11 billion light years from us. When we look at the close-ups, we see lots of different galaxy collisions. So we've looked at Hubble and Spitzer images from all over the sky, looking at different distances from us, which corresponds to different times throughout the age of the universe. And at all of those times and in all of those orientations, we see galaxy collisions. So this tells us that galaxy collisions are happening everywhere all the time, not just, ooh, there's one right here and it's kind of cool. They're all really cool, but they happen all over the place. So to sort of end out this section, I want to talk about supermassive black hole. So galaxies contain supermassive black holes. Some of them are very active, and we call that an active galactic nucleus. And it is shooting out the jets. We looked at these jets a couple of chapters ago. But I want to point out that the particles in the jet disrupt star formation. And so they can arrest new star formation in a galaxy. So just because the galaxy is very active with lots of dust and clouds and, all the things that should lead to new stars, doesn't necessarily mean that that will happen. If that galaxy is a very active galaxy, then you're going to end up with star formation disrupted by those jets. And once again, I keep talking and talking, so we're going to save this one and start the next video.